Whatever we do will be a good review, but may not be everything. So, bless you. Always go back and study your notes to add more to your cheat sheet if you need it. Thanks. So, with section 6.1, I'm going to, I think, do just 2 examples. And you should have your quizzes back from this section, so you can kind of use those to help you study as well. But this is what our directions will say. I think this is a pretty quick section. I think we just did it in one day. It says simplify using, or simplify each radical expression. Then it says use absolute value symbols when needed. In my opinion, that was probably the hardest part of 6.1, just trying to remember when you need to put absolute value symbols in your answer. So I'm going to review that with you here in just a minute whenever we get there. So first one, it says the square root of 25x to the 6th power. 25x to the 6th. Now, anytime you take a square root, or really any kind of root, of a product like this, you are allowed to break each part up. You can take square root of 25 times the square root of x to the 6th. You're not allowed to break it up like that if there's a sum or a difference underneath, but that's not what we have, so we should be good. Now, what is the square root of 25? 5, we got that. And I think everything worked out nicely in 6.1 as far as your exponents go. Remember to simplify something like this. This is a square root, and even though we don't write the 2, technically there is a 2 there. And to simplify that, we would just take the 6 divided by 2, which gives us a 3. So that says 5x to the 3rd power. Now, here comes the rule about absolute value symbols. If you're making a cheat sheet, you might want to write this down. And it says when you take an even root, so a square root, a 4th root, a 6th root, something like that, when you take an even root and get back an odd power, include absolute value bars around the odd power. When you take an even root and get back an odd power, include absolute value bars around the odd power. And the reason for that is because you can't take a square root or a 4th root or any kind of even root of a negative number. So those absolute value bars are just trying to keep everything positive. And that just happened here. We took an even root, that was technically a 2 there, even though we don't write it. We took an even root and got back an odd power. And so I'm going to go ahead and put those absolute value bars just around x cubed. So final answer, 5 times the absolute value of x cubed. Now, we'll try one more here in section 6.1. But it's not an even root, so you won't have to worry about absolute value symbols. This is just a cube root, bless you. And while I'm thinking about it, I will go ahead, I don't know if I still have them up here, surely I do. I will go ahead and give you that list of nice square roots and cube roots. Here they are, square roots and cube roots. I'll pass one of those out to you for the test on Wednesday. But I know some of you can probably just use your calculator to help you with this. Cube root of 27, we can work on that part first. Then we'll have the cube root of c to the 6th times a cube root of d to the 9th. You may not always have to write those steps out, but I'm just showing you that we're working on each term separately. So what is the cube root of 27? 3, yes. And for these, 6 divided by 3 is 2, so that's now c squared. 9 divided by 3 is 3, and that is now d cubed. It wasn't an even root, so you don't have to worry about absolute value. Okie doke. Everything worked out pretty nice in 6-1, except for this part. Any questions about those two? All right. Well, when we move on to 6-2, this is where the problems got just a little bit more complicated. So I'm going to do a little bit more in this section than I did in the last section. But here's something that's kind of nice. Simplify and assume all variables are positive. Assume all variables are positive. That means you don't have to have absolute value bars. I may actually write that down up here. That way, in case this is what you run into on the test, that kind of looked like an 11, but I tried to spread it out a little bit. That just means you don't have to worry about absolute value bars. Everything is going to be positive. Okie doke. So this will be number 3 for us. And number 3 has cube roots. It's the cube root of -7 times the cube root of -49. On your calculator, you probably could just type all of that in at one time. If your calculator is kind of weird and you can't really do, or it doesn't show you 2 steps at once, then here's another way to do it. Because these are the same types of roots, cube root, I can just go ahead and multiply the numbers underneath. If you take -7 times -49, that should give you 343. And now, again, this might be on our list over there, but if not, we went through how to do cube roots on our calculators. If you can't remember how to do that, let me know. But cube root of 343, that does just work out to be a 7. Okie doke. So again, you may have done that part. You may have just typed all of that in at one time. Now, let's try a little bit more here. Number 4, this is the square root of 125 times the square root of 32. I'm going to try and do this one like I did that one. I'll take 125 times 32. That gives me 4,000. But when I try to take the square root of 4,000, it gives me back a decimal that never ends. And you could take that and try to break it apart using some of our nice square roots. But that's a pretty big number to work with, and our list I think only goes to 10 or 11. So I'm going to come back over here, and maybe I should take these smaller square roots and simplify those first, and then we can hopefully put it all back together. Now, what would be the biggest nice square root that goes into 125? 125. 25, yeah, but you've got it. 25 times 5 is 125. So those are under a square root. I'll keep going with that here in a second. And then what's the biggest nice square root that goes into 32? It's not 4. 16. Let's do a square root of 16 times the square root of 2. Now this is 5. Square root of 5, I'm leaving that alone for right now. This is 4, leaving the square root of 2 alone. Then I can take the numbers that are not under a square root, I can multiply those out front, and then I can multiply the numbers that are under a square root together, and that would be it. 20 square root of 10. That would be our final answer. Alrighty, any questions about those? Now, we also had problems in this section with variables. And again, they don't work out quite as nicely in this than they did in 6-1. So we'll have to figure this out. It's the square root of 63a cubed. Square root of 63a cubed. I'm going to break it apart and kind of look at each little thing separately. I've got square root of 63, and then I'll multiply that by the square root of a cubed. So square root of 63 is not a nice square root, but what is a nice square root that goes into 63? 9. Let's do square root of 9 times square root of 7. Now 3 back here, the exponent, 3 cannot be divided by 2 nicely. So we're also going to have to break that square root apart. Now thinking about what we need first here, 3 can't be divided by 2, but what is the next biggest number less than 3 that can be divided by 2? 2. Yeah, it doesn't always work out to just be the number, but a lot of times it does. And then a squared times a, that's the last part that we would need for the a cubed. So going through the rest of this, square root of 9 is 3. Square root of 7, I don't know, I have to leave that part alone. Square root of a squared is a, and don't worry about absolute value bars here. Everything is positive. Square root of a, I don't know what that is, so I'm leaving that part alone too. Now, 3a goes out front because those are not under a square root. And then 7a, those can come together under the square root. That would be it for number 5. Alrighty, any questions on that one? I think I have one more in this section. It's a doozy. Number 6, a little bit more going on here. There's numbers in front and they're cube roots. So 2 times the cube root of 4x squared y squared times 2 cube root of 9x to the 6th y. All right. 2 times 2. Hey, I got that part done. 2 times 2 is 4. Let's go ahead and put that number in front. And because both of our roots are cube roots, we can go ahead and multiply together everything underneath. So I've got the cube root set up. Now 4 times 9, that would be 36. X squared times x to the 6th. What do I do with my exponents when I multiply with the same base? I add them. Very good. That is x to the 8th power. And same idea with the y's. You can think of that as y to the first. So 2 plus 1 is 3. Now the 4 is going to have to stay out front for a little while. And in the meantime, we're going to try to break down everything under the cube root. Be careful, it's a cube root. So cube root of 36 is not going to work out real nice. We'll see if there's anything we can do to that. Cube root, I'm just breaking all of that apart. Then I've got cube root of x to the 8th, cube root of y cubed. Okay, well, 4, still there in front. Now I'm thinking of cube roots. Are there any nice cube roots that would go into 36? If you don't have your list in front of you, you got cube root of 8, cube root of 27. Those are really the only options less than 36, and neither one of those work. So that's kind of a big number, but we have to just leave that part alone. You can't break down a cube root of 36. Now, next part, 8 can't be divided by 3, but what is the next biggest number less than 8 that can be divided by 3? 6. So what am I going to have to put under the cube root right after that? X squared, yes, x to the 2nd power. And then this part works out just fine. 3 divided by 3 is 1. Now, I see a lot of times students will get problems wrong because they leave the square root around something that shouldn't have a square root anymore, or a cube root in this case. The y does not have a cube root anymore because you did it. You worked it out nicely. It's just y to the 1st, or just y. So I'm going to leave the 4. I'm going to leave the cube root of 36. I still need to get that part simplified. Now I can take 6 divided by 3 to make that x to the 2nd power. And everything else I'm just going to recopy. So the only thing I did from here to here was fix up that part. Now, whatever is not under a cube root, that stuff can go out front. Then I have the 36x squared underneath. The answer is pretty messy on this one, but that would be it for number 6. All right, any questions about that? I'll leave that up there for a second in case you're still getting it. As far as the test goes, probably going to expect more problems from 6-2 than 6-1, just because 6-1 I think was pretty quick. There was a little bit more going on in section 6-2. Okie doke, I'm going to go ahead here. Stop me if you have any questions. Oh, I guess this is still a little bit of 6-2. Yeah, one more thing here, then we'll move on to 6-3. April Fools, in case you thought I was still, moving on to 6-3. Okay, all right, that wasn't a very good one. All right, to rationalize a denominator. This is the last part, finally, of 6-2. Remember, the goal for rationalizing a denominator is to get rid of roots in the denominator. You don't want to have any more roots, whether it's square root, cube root, none of that, left in your denominator. Okie doke. Now, I think if you look back at your notes from this stuff, I gave you a couple rules about doing this. One rule was this, how to do it if you have a square root on bottom. Another rule was about if you have a cube root on bottom, but I'm going to give you a hint about the test. You won't have to rationalize with cube roots on bottom. That was like a whole nother thing. The rule for that was completely different than the rule for this. So again, if you're looking back through your notes, there's two parts really, but all you need to know on the test is how to rationalize with a square root on bottom. Hello, thanks. We're reviewing here, section 6.2 for this part. Then it says for the rule, if you have a square root on bottom, multiply by that very same square root on top and bottom. If you have a square root on bottom, multiply by that very same square root on top and bottom. So again, this is from your notes. This is a rule straight out of your notes, but I left off the part about cube roots because you won't have to rationalize with cube roots on the test. All right, well, let's try one. This should be our last example from section 6.2. It says in the directions to just rationalize the denominator. By the time we're done with this, we should not have any more roots in the bottom of our fraction. Looking good. We'll try one of these. Number 7, square root of 10 divided by square root of 5x. Hi, thank you very much. We're doing some review here. This is 6.2 that we're in. Now I'm following the rule, and the rule said that when you have to rationalize with a square root on bottom, multiply by that very same square root on top and bottom. Now I'm going to do the bottom part first because it's the easiest part. So square root of something times the square root of the same something is just the something. And so that's why we chose to multiply by 5 square root of 5x on top and bottom, because I knew that would get rid of the square root. On top, you end up with the square root of 50x. Now, we want to try and simplify this as much as possible. If you think about the square root on top, you can, I gave it away right there, but you can break down the square root of 50. Let's take a square root of 25 times the square root of 2 times the square root of x. You can't really break down the x any further. And 5x is still on bottom. So when I put all this back together, this turns into 5. And then 2x, those can just go together under the same square root. And I know it's tempting. We could actually cross out the 5s here, so that works. But it's tempting to also cross out the x's. You can't do that because that x is under a square root and that one is not. So 5s can go, but x's have to stay. We'll have to leave it as square root of 2x all over x. Okie doke. It's basically like simplifying, but in the midst of simplifying, we also had to rationalize our denominator. Any questions on number 7? Now, when we move on to 6.3, we rationalized denominators again in the next section. So this will kind of come back to us a little bit toward the end of section 6.3. So this is the last section we'll talk about today. Tomorrow we'll do 6.4 to 6.7. Alrighty. Directions, I got a rule here first. You can write this down again, or if you don't want to, I understand it should be in your notes somewhere anyway. but it's pretty important. It says in order to add or subtract, radical expressions, meaning something with a root, they must be the same type of root. In order to add or subtract radical expressions, they must be the same type of root and have the exact same thing under the root. It's like getting like terms. So exact same type of root, both square roots, both cube roots, whatever, but they also have to have the same thing under the root. Good stuff to remember. All right, directions pretty short and sweet. Once you get that down, it just says to simplify. That is it. Now, there were a few different types of problems in 6-3, so I'll try to hit on each thing just a little bit. Number 8, this shouldn't be too bad. 3 square root of 5 minus the square root of 5. It's kind of like if you had 3x minus x. You don't just get rid of the x's. This is kind of like a 1x. So 3 minus 1, that would be 2x. Same idea up here. You don't really do anything with the square root of 5s. Those are just kind of labels, like the x's were down here. Take the 3 minus the 1, and you can just make that 2 square root of 5. You're allowed to do that because these are the same type of root and you have the same thing under the root. So they're considered to be like terms. That would be our answer then for number 8. Looks good. Now moving on to number 9. Not working out as nicely here. The square root of 192 plus the square root of 27. Okay, I see some of you searching for your papers here. If you don't have them, I can give you another copy here in just a little bit. But you're right. These are not the same thing. This is something that could not be combined. They are both square roots, but they don't have the same thing under the square root. So these are, especially this one, these are pretty big numbers, which means we might be able to break them down a little bit to get them to be like terms. Now, using our list of nice square roots, I'm going to try to find the biggest nice square root that'll go into 192. Now, before I start trying out a bunch of numbers, has anybody found one? 64. Thank you for saving me some time. 192 can be divided by 64. You should get back a 3. If you're not sure how to get that, just take your calculator and start trying out numbers. 192 divided by 81. No, 192 divided by 64. You should get it pretty quickly, but that will work out nice. Now this one, not as hard to think about. The biggest nice square root that goes into 27 should be 9. Now, if you turn this into 8 square root of 3 plus 3 square root of 3, by golly, now they are like terms. They both have a square root of 3, so we can just add those numbers out front. That will just turn into 11 square root of 3. Even if they don't end up being like terms, you still want to do this part where you break them apart, because the directions just said simplify. So you want to go as far as you can. Okie doke. I think I've got number 10 over there. And if you're trying to think about the room on your cheat sheet right now, number 12. I think I'm going to 12 today, and that will be it. This one says, cube root of 375 plus 3 times the cube root of 81. 375, here I go. I'm looking at cube roots, and I'm just gonna start dividing them out. I've got 216, that won't work. 375 divided by 125, that does work. I got back a 3 from that. So I want to break that apart into the cube root of 125 times the cube root of 3. I'll come back to that stuff here in a second. Now there is a 3 in front here. It'll just kind of stay out front for a little bit, but let's think about 81. Are there any nice cube roots that go into 81? Yes, that will work. So here's the 3, but now we need cube root of 27 times cube root of 3. Now let's think about what all this is going to be here. Cube root of 25 is 5. You can go ahead and put that with the cube root of 3. Now, if you want to look ahead a little bit, you can. I'm just going to do one thing at a time, though. Leave the 3 there. Then, cube root of 27 is also 3. We've got 3's everywhere up here. And then cube root of 3 is still in the back. So, these two numbers right here can get multiplied together. That's going to end up being 9 cube root of 3, and you may have done that without even showing this step, and that would be fine, but now they are like terms. Cube root of 3, cube root of 3, so I'll add the numbers in front, and that makes 14 cube root of 3. Again, even if you do all that work and you still can't add them up, it's fine. You still want to simplify the roots as much as possible. Any questions on that? Alrighty, 2 more here. Number 11, kind of hard to see those square roots, but it's got 2 plus the square root of 7 times 5 plus the square root of 7. What do we always do in math when we multiply binomials?
FOIL.
Yes, we FOIL them. So let's do that. 2 times 5 would be 10. Now we haven't really multiplied with roots yet today, so watch carefully here. When I take 2 times square root of 7, the 2 is not under the square root, so you kind of just have to squish those together and make it